So, because we were discussing that actually in the Kohn-Sham DFT, we will solve the equation just like what you will do in a Hartree-Fock. So, it may be interesting to see what is the similarity and what is the difference in the Hartree-Fock and Kohn-Sham DFT, especially due to the fact that both actually works in a single determinant picture. Although the DFT itself by philosophy only is supposed to work on the density, I have bring back the determinant picture, determinant made out of orbital, because I do not have any other way to get out the kinetic energy. So, at least I can fit the kinetic energy by using the orbital which corresponding to a non-interacting system, and rest I can push it to the exchange correlation function. Now, what does it really mean? So, what are the similarities then? First of all, it is a common variational principle. In case of the Hartree-Fock, I was changing the orbitals which was giving me the best possible energy. So, I will change the orbital, I generate a select determinant, and I will find out which will give me the best possible orbital energy. In the Kohn-Sham DFT, of course, I will not vary the orbital as it is. I will varying the orbital, but in a backhand way, because I am using an orbitals corresponding to a non-interacting system. The variation in the density can actually result in the variation in the orbitals. Now, kinetic energy and nuclear attraction component of the K matrix, which is the Kohn-Sham matrix, is actually identical with that of the Fock. They are the same form, same equations, everything. Now, if the density in the classical inter-electron repulsion is expressed in terms of the same basis function used for the Kohn-Sham orbital, then same 4 index external electron repulsion integrals will appear in the F. So, the problem of n to the power 4 scaling in Hartree-Fock comes due to the 4 electron integrals, 4 index integrals, and that actually scales as n to the power 4. In the Kohn-Sham also, if I just express the classical inter-electronic repulsion, the Coulomb term in terms of the same basis function as K's orbital, this will also look very similar with 4 index integrals, and density is required for the computation of secular matrix. Remember, in the case of Hartree-Fock also, you are actually rewriting the Hartree-Fock equation in terms of charge density bond order matrix. So, quite similar. Now, density determined from the orbitals obtained from the solution of the secular equation. This is same both in the case of Hartree-Fock as well as Kohn-Sham theory, and Kohn-Sham procedure is actually an SCF iterative procedure. So, I will start with a gas density which will correspond to some gas in the orbital density. I will form the Kohn-Sham matrix, diagonalize it, get a new set of orbital, new set of density, and we will go like that. So, we will come into this algorithm, actual algorithm, just in a while. So, the Kohn-Sham procedure is actually in terms of programming, it is a SCF, same as SCF iterative procedure. That is why historically density functional theory codes are actually implemented by modifying the existing code for a Hartree-Fock calculation. So, if you have an Hartree-Fock calculation, and if you somehow get the code to calculate these functional derivatives, you can actually easily write crude, rudimentary but correct Kohn-Sham DFT code. What is the difference? DFT is derived so far contains no approximation, it is exact. If there is an approximation, it is in the exchange correlation functional. If I get the exchange correlation functional, this is exact. But we need to know the exchange correlation function as a function of rho, that we do not know. Weinberg-Kohn theorem only says that there a functional must exist, but how the functional looks like, what is the exact form, Weinberg-Kohn theorem is actually silent on that. So, no guidance, although what the function looks like, although a variation theorem exists, but it still do not tell how the function actually looks like. So, what is the contrast between Hartree-Fock and DFT? Hartree-Fock is an approximate theory. Remember, it's approximate the exact wave function by a single discrete determinant. But the equations what is obtained by taking these single set determinants, they are solved exactly. So, it's an approximate theory solved exactly. Whereas the density functional theory is an exact theory. If you know the form of the exchange correlation function, this is an exact theory, there is no approximation. However, the relevant quantities are solved approximately because the form of the operator is not known. So, Hartree-Fock, again I will repeat that Hartree-Fock in an approximate theory is solved exactly, DFT is an exact theory solved approximately, as simple as things can get. Exact DFT is of course variational. So, if I know the form of the exact exchange correlation function, it is a variational, but when approximation of exchange correlation functions are used, this is no longer true. So, for most of the DFT calculations I will do, it will not obey variation theorem, and that sometimes often is a misconception, because I am still solving like a Hartree-Fock self consistency procedure and I am iterating over the orbital. This does not mean my density functional theory energies are variational. So, to calculate properties I need to be really careful. Good thing is that both exact and approximate DFT are size extensive. What does it mean by size extensive? The energy actually scales correctly with respect to the system size. This is an advantage because even in approximate format it is size extensive. So, this is not a problem like CI or truncated CI. And remember, density functional theory, the way it is constructed, although it is a single determinant theory, it still actually includes the electron correlation effect because it is written in terms of electron correlation. Now, if I go to the algorithm and try to solve the SCF self consistency procedure, how it will go through? So, I will choose a particular basis set, I will choose a molecular geometry, compute and store all overlap of one and overlap integral and one electron integral. This is up to now, this is same as Hartree-Fock. I will guess the initial density matrix P0, that is what we are also doing in the case of Hartree-Fock. So, I can use an H-core approximation, a completely non-interacting system. Then I will construct and solve the Kohn-Sham secular equations. I will construct the density matrix from the occupied Kohn-Sham MOs. I will check the new density matrix if it is sufficiently similar to the old density matrix. If yes, then I will come out of the loop. If no, then I will again go back into the previous step. I will construct the solve the Kohn-Sham secular equation, and I will reiterate and go through these loops. The moment the density matrix from a particular step is very similar to the previous step to some cutoff, I will just get out of this loop, and then of course I can find out if I don't want to optimize the geometry, I will just come out and print the certain things. If I want to optimize the geometry, I will check the geometry optimization algorithm, calculate gradient, go to the new geometry, again calculate the compute and store all overlap and one electron integral, do the SCF procedure to get again solve, and we will go like this up to the time the geometry is not converged. So, here there will be two loops, one for geometry and one for the density functional theory iterations. Now, some practical consideration. First thing is that in the Hartree-Fock theory, number of Coulomb integral requires evolution is n to the power 4. So, as it is, the scaling is n to the power 4, we can use approximation like Rij cos x to reduce its formal scaling, but if I do not use any approximation, it is n to the power 4. DFT it can be reduced to n to the power 3, where n is the number of Kohn-Sham atomic orbital basis function, if you approximate it properly. And this will lead to difference in the computational scaling for pure and hybrid functional, because how you are taking the exchange. So, after the basis set and the molecular geometry choice, the overlap integral, kinetic energy and nuclear attraction integrals are computed, same as Hartree-Fock and DFT. Hartree-Fock construct a density matrix, then compute 2 electron integral Coulomb and exchange, whereas in case of DFT, construct the density matrix and also construct the exchange correlation functional, evaluate the remaining integrals in the Kohn-Sham matrix element. Now, this involves evolution of exchange and integrals involving exchange and correlation energy. And this evolution of exchange and correlation energy over densities in DFT is generally, it cannot be done analytically, it has to be done numerically on a grid. And so that mean actually the accuracy of a practical DFT calculation depends upon a lot on the grid size you are using. In ORCAD, default grids are used unless otherwise specified by the user, but for a practical computational chemistry consideration, it sometimes is very important to go into the grid size and check your calculations has converged with respect to the grid size or not. Change in the grid size can lead to some changes in the total energy, which is fine, perfect, but the energy difference, the bond and the geometry may not has to be same. If it is not converged with respect to the grid size, then you have to change the grid size and check the convergence. In most of the cases, there is a prior literature or ORCA manual, you can find out what is the default grid size for this kind of calculation. Problem is that if your grids are not proper, you remember that like the integration of the full density should give me number of electron. If my grid size is small, then it will not lead to the number of electron, it will be slightly smaller than that, and this can lead to sometimes convergence issues. So, one need to be really careful about the DFT grid sizes. We will see an practical computation example where we will calculate the energy of the DFT functionals with different grid size, and we will see how the differences looks like. But before going into that, we need to discuss a little bit about more kind of functionals. So, up to now what we have discussed is mostly LSDA, and we will see some benchmark number to check how the numbers actually looks like. Are they better than Hartree-Fock, worse than Hartree-Fock, and then we will see how to improve it. Remember, it is not strictly true that there is no way to improve DFT functionals. There are some recipes available already, and the recipes are very physically meaningful, that how you can improve the DFT functions. But problem is that just improving using one of the recipes does not always lead to good answer for all the properties. Remember, when I have to improve the functional, every property should come should come more accurate, which is the case in the case of wave function based methods. If you use couple cluster, if you go from CCSD to CCSD-T, every property, dipole moment, bond length, binding energy, Hessian, IR frequency, excitation energy, everything will come better. That is very difficult to do in DFT. Even these recipes provide some recipe for improvement, it will not lead to improvement in all the properties. So, next we will see in the next lectures, we will see how to improve upon the LDA or LSDA and how to get much better numbers, and you will come to know some systematic improvement about the DFT scheme, and we will do some practical computation. Of course, if you do this once your all the integrals are calculated, remember Hartree-Fock and the Kohn-Sham is actually same. So, whatever difference is in the speed of Hartree-Fock and DFT is basically in the integral calculation. Once your integral calculation is done, they are of very similar computation cost and will take very similar time. So, now you see the advantage. I am still working in a single determinant picture. So, actually have a scaling n to the power 4, n to the power 3, and I am getting energies which will be much more accurate because I contain correlation. Whereas, in the case of wave function theory, the lowest cost you will pay to include correlation, that is a second order molar placid perturbation theory, is still n to the power 5 and with a big storage requirement. So, DFT for practical calculations is always much better.